Good day, everyone. In this lecture, I'm going to discuss the definition of topology and give some examples to illustrate the concepts. Now, what is a topology? Let me consider this definition. First, we let X be any non-empty set. And then we have here class tau of subsets of X. We call this tau a topology on X if and only if it satisfies the three conditions here. First condition, X and empty must belong to the class tau. And then if we are going to get the union of any number of sets in tau, the union must belong to the class tau. Then the last one is, if we are going to get the intersection of any two sets in tau, so intersection belongs to tau. Now take note here that these three conditions here are very important. If any one of the three conditions is not satisfied, then the class tau is not a topology. So if in the case that the three conditions are satisfied, so tau is a topology, then the members of tau are then called tau open sets or simply open sets. And then X together with tau, we have here the pair X tau is called a topological space. This is the notation for a topological space. Now, let me consider this example here. We consider X be equal to this set with elements A, B, C, D, and E. Then we have here the class of subsets of X. So we will show if it is a topology or not. So we will be using the three conditions. We will be showing rather the three conditions. So in the first condition, obviously X and empty are in the class of sets here. So condition number 1 is satisfied. Now let's have condition number 2. So we are to get the union of any number of sets in this class. So we can take two unions, 3, 4, and so on. Any number. So let's have here first X and empty. So X and empty, union of X and empty is of course X. So any sets union of X is X. Now let's have here an empty set. Empty set union any set in the class is of course the set itself. And then let's try this one. This set union this set is the set with elements A, C, D. If you're going to get the union of this, so of course A, C, D is in the class. Another one, if we are going to get the union of this set to this set, so still this set. And then union of this to this is A, B, C, D, E. And A, B, C, D, E is the set X itself. So X is in the class. So let's proceed to this one. So the union of these two sets here is this set. And the union of this set to this set here is this set. And of course, it belongs to the class. So let's have this one. The union of this one to this set is A, B, C, D, E. And it is X. So notice that if we are going to get any number of sets in the class, the union of it is in the class itself. Therefore, in that case, condition number 2 is satisfied. Now, we only have the last condition. Okay, for the last condition, we are going to get the intersection of any two sets in the class. And we will show if that intersection belongs to the class. So here, the intersection of X and empty is of course empty, intersection of x and this one is this set. So the intersection of x to any set here is the set, smaller set. Then here we are to get the intersection of empty and any set here. Of course, the intersection of empty and this set is empty. Intersection of empty and this set is still empty. So the intersection of empty to any set here is empty. Now let's have this set here. So the intersection of these two sets here is of course empty because there is no common to the two sets. So of course empty is in the class. Another one here, intersection of A to this set here, ACD, intersection A is of course A. So A is in the class. Another one, A, intersection this set is empty, and empty is in the class. So let's move to this set. The intersection of this set to this set is CD, right? CD. So CD is the set with element CD is in this class. Then here, intersection of this set to this set is of course CD, the set with elements CD. Now let's have this one. The intersection of this set to this set is CD. Okay, CD, the intersection. And we know that the set with element CD belongs to this class. Now, as you notice that if we get the intersection of any two sets in this class, it belongs to the class. Hence, the third condition is satisfied. So in that case, since we have shown that the three conditions are satisfied, so we can say that this tau sub 1 here is a topology on X. Okay? Since tau 1 is a topology on X, therefore the members of the class, we have X empty, and these sets here are tau sub 1 open sets, or simply they are just called open sets. And the pair X tau sub 1 is a topological space. Okay. Now, let's have another example here. We will consider the same set X, but we have another class of subsets of X. Now, we will show the three conditions. So, first condition, X and empty are in the class. So, the first condition is satisfied. Then, the second condition, we will get the union of any number of sets in this class. So if we are to get the union of this, the union of X in any set, of course it belongs to the set because the union is X. Then the union of empty to any set also belongs to the class, class. And then if we get the union of this, the union is ACD. And ACD, the set with elements ACD belongs to this class. Another one here, still ACD. Then here, A, B, C, D. Oh, take note, if you are to get here, if you are to get the union of A and this one, this set, the union is A, B, C, D. And take note, A, B, C, D is not in the class. So here, the set AB with elements A, B, C, D is not in this class, tau sub 2. Hence, we can say that the second condition is not satisfied. Now, in that case, again, if any one of the three conditions is not satisfied, then the class, we call the class, or then the class is not a topology on X. Therefore, we can say that tau sub 2 is not a topology on X. So that's it. By the way, in my next video, I'm going to discuss about some examples of topological spaces.